take up lecture 10, which deals with properties of surfaces. So far we have been talking about forces and moments, and today we will be slightly deviating from those concepts and we will be discussing surfaces. Now, in earlier lectures, maybe lecture 5 or 6, we were talking about equivalent force systems, and also in some of the problems we discussed with triangular distribution of force or rectangular distribution of force in context of beams, etc. These are also some kind of surfaces, and we replace those distributions with their equivalent single force concentrated at a point. So, all these facts emerge from the properties of surfaces. Now, whenever you want to buy a plot of land or in some other context, you know that the size of a surface is given by by its area, and then the shape is given by whether it is triangular or circular or trapezium, etc. Orientation, you can describe that this piece of land is south facing, etc. But to put these concepts in a quantitative fashion, we need some analytical properties which we will be discussing now. Well, I have given here some measures. Some of them are quantitative measures that they can be expressed in numbers. The others are qualitative measures. We have already talked about area, which is a measure of size of a figure or a plot of land, etc. And then in the qualitative measures we had shape. Again, just like we can talk of a circular area or a triangular area, and to put it in a quantitative manner, different shapes or orientations, we can use or rather get some information by using first moment of area, second moment of area, etc. Let us look at this example. Here we have a rectangular area of or a square area of size, each side A, so its area is A square. On the right hand side we have a triangular area, the base is 4A by 3 and the height is 3A by 2. Again, if you calculate its area, it will again come out to be A square. So, both these areas are of the same size, but quite naturally, quite obviously they are different. If we take the first moment of these two areas, they will come out to be different. There may be a case that two areas have the same two figures have the same area as well as the same first moments, then the second moments may be different. If the first the size, first moment, second moment are also equal, then the third moments will be different, and so on and so forth. So, the higher we go in taking the moments, more and more distinction we can make between the given two areas. So, first we will start with the first moment of an area. Here is an arbitrary figure. Well, we can calculate its area graphically, or if the figure is well described by an equation, we can with the help of area integrals we can find out its area. To get the first moment of this area or of this figure, suppose we consider a small element of this area of the size dx along x axis, dy along y axis. So, that small area is dx by dy. Then from the center of this rectangular area, the distance of the y axis is x and distance of the x axis is obviously y. So, we will define the first moment or simply moment about x axis, which we will designate as mx, is equal to the area integral y times dA. dA is that small area. So, we multiply this small area with the distance from the x axis, that is, this is y, and it can be also written as, for rectangular Cartesian coordinates, area integral of y dx dy. Okay. Similarly, we can define the moment about y axis, which is my, and this will be the dA, the infinitesimal area dA times x integrated over the entire figure, and it can be written again as x dx dy integration over the area. Well, now immediately connected with the moments of area, we have the concept of centroid of an area, and here I would like to draw an analogy between centroid of an area and something we have already learned, that is the center of pressure. Suppose there is a given area and some fluid pressure is acting on it, and it is acting in a normal direction to the area. Then you remember we replace that distributed force system with an equivalent force, a single concentrated force acting through a point which we call center of pressure. Similarly, if we consider any body under the gravitational field, then the whole weight can be considered to be acting through a single point, namely the center of gravity. So, similarly over here, once we have the given figure, then we can concentrate the entire area of that figure through a single point called the centroid of an area for the purpose of calculating the first moments of that area. So, the x coordinate of the centroid xc is equal to the first moment about y axis, okay, divided by the entire area. Or you can say that the first moment about y axis of the figure is equal to the total area times the distance xc from the y axis. And similarly, for y coordinate of the centroid, namely yc, we have the first moment about x axis divided by the entire area of the figure. Now, this property of centroid, that is it is described by xc, yc, is independent of the choice of coordinate axis. To illustrate this, let me show you the next figure. Suppose here it is, a given figure is there, and using the definition of centroid in the coordinate axis x and y and z is perpendicular to the plane of the screen, we have located that the centroid is at point C. Now, let us say we rotate the coordinates through an angle theta. So, that this is theta and this is also theta. Okay. So, the new coordinate system is x dash, y dash, and of course, z dash is parallel to or is coinciding with the z, and it is normal to the plane of the screen. Now, if we use the definitions of the first moments, we can again calculate x, the centroid in the new coordinate system, that is xc dash and yc dash. Although numerically they may look different, but if I plot them, these two coordinates xc dash along x dash axis and yc dash along y, again the same point will be obtained, that is same point C. Okay. So, it means that during rotation or as a result of rotation, the centroid, the location, the absolute location of point C has not changed. In this example, the origin was same, but only rotation was given. Suppose now I change the origin also from O to O dash. Then again I go through the same definitions and calculate the x double dash c, y double dash c. Again they may look different, but when I plot them in this coordinate system, again I will get the same point C. So, what does it mean? That it means that whatever coordinate system you may use, as long as they are rectangular Cartesian coordinates, the location of point C will be invariant, it will be unchanged, although the individual values of the x coordinate or y coordinate will be different, but after plotting it you will get absolutely the same point. Of course, if your calculation, you are not making any calculation errors. Okay. So, this is a very important result, that is, the centroid does not depend upon the choice of coordinate system. Let us consider an example. Here is a given area which I can show you over here. This is the area. Okay. And on one side there is a vertical line, horizontal line, and the other line, the third side is a curve given by an equation y square is equal to ax plus b. So, it is a kind of curvilinear triangle. Now, it is also told to us that it is this curved side is passing through a point on x axis at a distance 0.4 meters from the origin, and also it is intersecting the height at a distance of 1 meters from a line, along a line at a distance of 1 meter along x axis. So, these two points are given on this curve. So, the curved edge of the area shown below is described by the equation where a and b are constant. Find the area and its moments about x and y axis. That is our what we have to determine. First of all, we have to determine the constants a and b, so that we know the equation completely. And since this point 4 lies on this curve, so if we substitute x for 0.4 and y is 0 at this point, so 0 is equal to 0.4 a plus b, this is first equation, and then I go to this point whose coordinates are, you can easily see 1 comma 1. So, if I substitute x is equal to 1 and y is equal to 1, I will get a plus b is equal to 1. So, these are two equations, simple equations from which I can obtain two unknowns. So, they are found to be a is equal to 5 by 3, b is equal to minus 2 by 3. So, substituting back the values of a and b into the equation, we will get 3y square is equal to 5x minus 2. So, this is the equation of this curvilinear edge. Now, to obtain the area of the figure, well, we have to use the area integration. The area, infinitesimal area, you can imagine is, we have already done dx into dy. Now, I am using it instead of y dash, because y is the upper limit of the integration on y dash. So, to make a distinction between the variable and the upper limit, I am using y dash. So, first I integrate the inner integral. So, this will give me y dash into dx from limits 0 to y, and on substitution I will get y dx from 0.4 to 1. Okay, that is simple, and this has a very interesting interpretation. This y dx is the area of a strip of thickness, or rather width dx, and height is equal to y. Okay. So, you can alternately say that the total area consists of various strips of thicknesses dx and height y, depending upon where we are along this curvilinear edge. So, if we integrate now, this y is substituted from the equation of the edge, that is 3y square is equal to 5x minus 2. So, from here y can be easily obtained. You divide throughout by 3 and take the square root. So, which we have done, 5 by 3x minus 2 by 3 whole square root times dx. Now, this square root function can be again integrated and limits can be substituted to give us finally the result as the total area comes out to be 0.4 meter square. Okay. So, either you can use the strip integration or you can use the infinitesimal rectangle dx by dy and do the integration. Both are equivalent. Then we come to the moments of this area. First of all, I will take the moment about y axis, okay, about x axis. So, that will be area integral y dA. dA stands for dx dy. So, again you can carry out the integration. So, again y dash dy dash integral from 0 to y and x integration from 0.4 to 1. So, first carry out this integration on y square by 2, and then substitute for y square from the equation of the curvilinear edge, you will get this integral, and carry out the integration on x, substitute the lower limit and upper limit, you will get the moment as 0.15 meter cubed. Area was meter square obviously, and moment will be meter cubed. Well, finally, we go to the moment about y axis. So, by definition it is x dA area integral, and in the same fashion we come up to this integration. Okay. After carrying out the y integration and substituting for y square, we come to this integral. This integral is slightly complicated rather, and we take the help of integration tables. They are easily available in mathematical handbooks or sometime in the subroutines. So, you can get the result from the integration tables, and this will be the integration, and again we substitute the lower limit and upper limit, and we, after little calculations, we get the moment about y axis, first moment about y axis as 38 by 125 meter cubed. So, we have calculated area, first moment of the area, and the first moment of area about x axis, first moment of area about y axis. Mind you, in all these area integrals or moment integrals, we are using only plane areas. If the areas are curvilinear, shell type, like a paraboloid or a hyperboloid, etc., then they, of course, similar definitions will be applicable, but now the integration will be in the curvilinear coordinates, which is quite complex, and that is why We are not considering shell like areas. Okay. Now, let me make a very interesting observation. Sometimes we find areas which are symmetric about an axis. That is, if we can determine an axis such that if I place a mirror vertical to the area, then the right half of the area will be a mirror image of the left half or vice versa. For example, here this is an area, kind of figure 8, and about the y axis, if I put a mirror, this part is mirror image of this part. Sometimes you may have two axes of symmetry, that is x axis and y axis, both are symmetrical. So, in those two cases, our determination of these centroids can be very easy, or rather first we will determine the first moments and then we will come to the centroid. For example, I want to find out the first moment about y axis, and y axis happens to be the axis of symmetry. Suppose I choose a small infinitesimal area dA, then as I have said that due to its mirror image, there will be a corresponding area dA on the left side. If the distance of the right side area is x, then the distance of the left side area, so infinitesimal area, will be minus x from the same y axis. So, dA times x will cancel out dA times minus x, and that can be said for any other areas. So, for every area, every small infinitesimal area on the right side, there will be a corresponding area on the left side, but at a distance negative of the former one. So, there will be a pairwise cancellation of all these moments, and you will find that if y axis is the axis of symmetry, then my will be 0. If x axis is the axis of symmetry, then mx is equal to 0. And accordingly, if y axis is the axis of symmetry, then yc, that is y coordinate of the centroid, x coordinate of the centroid xc will be 0, and the y coordinate will lie anywhere along the y axis. If x axis is the axis of symmetry, then yc will be 0 and xc will lie along anywhere. And if the figure is such that it has two axes of symmetry and these two axes are mutually orthogonal to each other, you can choose them as x coordinate and y coordinate, and then you will find then the centroid lies at the intersection of these two coordinates, that is, it will be at 0, 0. Okay? So, symmetric figures are very convenient to work with. Now, let us take up an example to illustrate this feature. Suppose there is a semicircular disc. Okay. A semicircular disc of radius r is shown over here. Determine the location of the centroid. All right. Well, by the very definition of a circular area, two perpendicular diameters, or rather any diameter, is an axis of symmetry, and we will choose one diameter as the base of the semicircle and the other diameter perpendicular to it passing through the center. So, that is y axis. So, this y axis is the axis of symmetry. All right. So, we know that the centroid has to lie on this y axis. So, the x coordinate of the centroid is automatically known to be 0. Only we have to find out the y coordinate. Well, to find out the y coordinate, here we will take, instead of a rectangular infinitesimal area, we will take a curvilinear infinitesimal area. How do we get it? We will take any two radii and subtending an angle, very small angle d theta at the center. Here I am showing it in a exaggerated manner. This sector like shape is chosen so that it subtends an angle d theta at the center, and its inclination is of this sector like body is theta to the x axis. This side is dr, okay, and the center of this sector is at a distance of r, radius r from the center. So, if we find out the area of the semicircle, well, for the circle the area is pi r square. So, semicircle will be pi r square by 2, and then to determine yc we will have we want to determine this r d theta dr is the area of this shape, okay, and into y because y is the height, sorry, this height is y, okay, this height is y. So, and this y is equal to r sin theta, again this y is equal to r times sin theta, right. So, y r d theta dr divided by the total area of the semicircle. So, you can see that it is the area integral r sin theta r dr d theta divided by pi r square by 2. Now, to calculate the area integral, it is not difficult. We will have the distance, the radius going from 0, that is from the center to the outer periphery, that is the radius capital R, and theta angle going from positive x axis to the negative x axis, that is 0 to 180 degrees or 0 to pi. So, sin theta r square dr d theta divided by pi r square by 2. All right. So, first we will carry out the integration on r square dr, which will give me r cubed. So, if I substitute the lower limit and the upper limit, so r capital R cubed divided by 3 into the theta integration of sin theta d theta, and that will give me minus cosine theta, and finally we will have this as 4 r by 3 pi, right. So, what are the coordinates of the centroid? We have already seen that it lies along the y axis. So, x coordinate is 0 and the y coordinate is 4 r by 3 pi. So, this is how you will get the centroid of any figure, provided you know the shape of the figure or equation of the periphery or circumference of the figure. Sometime now we will come to slightly more practical problems, centroid of a composite area. In many engineering applications, the areas may not be simply a rectangle or a circle or a triangle or a trapezium, etc. But the areas may have some notches, some holes, or it is made up of two different rectangles, one rectangle, one circle, etc. So, all these areas are called composite areas. Now, these areas can be treated as a combination of, as I said, different areas, and for holes and notches we have to subtract those areas, that is, we will treat those areas as negative areas. How do we calculate the centroid of such areas? For example, let a given composite area be consisting of n number of simple areas, either positive or negative. Then the x coordinate of the centroid of the composite xc is equal to summation of the individual simple areas times the corresponding x coordinate of the centroid. So, after taking the summation, you divide by the total area. Similarly, for the y coordinates, that is, you take the individual simple area, multiply by the corresponding y coordinate of the centroid, sum over all the areas and divide by the total area. These concepts are very useful. These composite area, centroid of the composite area is very useful in a later course of solid mechanics, where beam theory, in analysis of beams, the centroid of the area of cross section is a very important concept, and it is very useful to know how to calculate the centroid. The centroid calculations for composite areas can be very conveniently handled with the help of tables. That is, we will do the calculations in a tabular manner, and to illustrate this, I have selected an example that here is a composite area. What it consists of, you can say that there is an outside rectangle of side 40 mm in one direction and 47 plus 35, that is 82 mm in the perpendicular direction. So, the length is 82 mm, height is 40 mm. Out of this rectangle, a circular, semicircular area has been cut out and a rectangular area has been cut out. So, this hatched area is the final figure for which we want to calculate the centroid. So, we will consider three areas. First is the area number 1 is the outside rectangle, as I said, of dimensions 8.2 into 4 centimeter square. Then there is a circular or rather semicircular area of radius 2.0 and centimeter, and then there is a rectangular area of 3.5, that is 35 mm and 13 mm. So, this is 3.5 into 1.3 centimeter square. So, the shaded or the area of interest is 1 minus 2 minus 3 areas, and we will take the origin for our calculation as the left hand lower corner of the figure. Okay. Now, area 1, 2, 3, we have first is the outside area. If you look at the figure, this outside area of dimensions 82 by 40, and its centroid will be, because of the symmetry, at the cross section, at the intersection of the two symmetry axes. So, it will be at this center. So, we will see first area is, well, instead of millimeters we are calculating everything in centimeters. 4 into 8.2, which comes out to be 32.8 centimeter square, and this x coordinate of the centroid of figure number 1 is half of the length, that is 4.1, area into x coordinate you have here. Similarly, the y coordinate of the centroid is half of the height, that is 2 centimeters, and this is a times y for that. Figure number 2, which is actually a semicircular notch, so it will be a negative area. So, negative pi by 2 into, so pi r square by 2. So, it will be minus 6.28. Now, we have already calculated the centroid of a semicircle. So, using that formula we will have 2.7 centimeter along your y axis, and this will come out to be this minus 16.956, and y axis of the coordinate of the centroid of the semicircle will be 3.15, and this will give me the moment as minus 19.79, and third figure is again a rectangle. Dimensions are 1.3 and 3.5, again it is a notch, so minus, and so you will have again the contribution along the x and y coordinates. So, what if I add up all these three areas taking into account the negative signs, then we will have the net area as area A 21.97 centimeter square, and the sum of these moments of these x moments of this area are 88.17, sum of the y moments are 42.86 centimeter square, is centimeter cubed. So, by formula for the xc and yc, when we substitute, we will get 4.01 and 1.951 centimeter as the coordinates of the centroid of the shaded area. So, this is how you can calculate for composite areas the centroid. Well, the concept of the centroid of area and the moments of the area, etc., that was for the two-dimensional figures. We can go to three-dimensional figures, that will be volume naturally, or one-dimensional figure which will be curves or lines. And these are also sometimes very useful in solid mechanics or in dynamics problems. Okay. So, as an extension of what we have done about areas, let us do the similar thing for volumes. So, center of volume, since volume is a three-dimensional concept, so we will be using the three-dimensional coordinate system x, y, z. So, the position vector of the center of a given volume is obtained by the, you consider an infinitesimal volume of dimensions, let us say in the rectangular Cartesian coordinates, the dimensions will be dx times dy times dz. So, this will be written as dv. The position vector of that, the center of that infinitesimal volume, that is r vector, and you integrate this over the entire volume and divide by the entire volume. That will be the center of the volume, where V is the entire volume of the body. Now, this is for volume. You know that volume into the mass density gives you the mass. So, here we have the center of mass, which is position vector RC m. This is position vector for volume, it was RC volume. So, definition is exactly similar to the center of volume, except that now we will have rho, that is the mass density, which can be a function of the position, that is the density is varying from point to point. If the material is non-homogeneous or a mixture, okay, let us say mixture of 2 or 3 types of metals, right. So, depending on whether you have metal 1 or metal 2 or metal 3, the densities will be different. So, for non-homogeneous densities, you have this definition as center of mass. The total mass, of course, is very easy to understand, rho times the infinitesimal volume integrated over the entire body, and obviously if rho is constant, that is material is now homogeneous material, that is every point has the same density, then this rho can be taken out and you can see that the center of volume will be equal to the center of mass. Let us consider an example to obtain the center of volume for this figure, 3-dimensional figure, which consists of a cylindrical part, a conical part, and a cylindrical cavity has been drilled out of it. Again it's an example of composite volume. The simple volumes are a cylinder plus a cone minus a cylinder, okay, and various dimensions are given, that is the length of the cylinder is 1.5 meters, diameter is 1 meter. Again the height of the cone or the length of the cone is 1.5 meters and base circle is 1.0 diameter, and for the cavity the diameter is 0.4 meters and the length of the cavity is 2 meters. Okay. So, out of total of 3 meter length of the bullet shaped body, up to 2 meters there is a cavity. So, we have to find the center of the volume for the body shown. Well, consider 3 volumes, cylinder of diameter 1 meter and length so much, cylinder of diameter this, so this is the negative volume, and the cone of base and length. So, calculations again are very easy to do in tabular form instead of otherwise. So, 3 volumes, 1 which is cylinder, 2 is cone, 2 is the cavity and 3 is the cone. So, its individual volumes are calculated. For cylinder, the base area times the length of the cylinder. Okay. So, pi by 4 into 1 square into 1.5, this gives me 1.1781. For the cavity, again because it is a cavity, minus pi by 4, again length is 2 meters, the diameter is 0.4. So, you will get minus has been missed out. So, this is minus 2.25433 and this is for the cone. Cone is 1/3 of the enclosing volume of the cylinder. So, 1 by 3 pi into 0.5, yeah, pi r square into length, that is it. So, these are now you can observe one thing very clearly, that this entire composite body is symmetrical about this x axis. So, x axis is the axis of circular symmetry. So, the centroid must lie along x axis. So, we do not have to calculate the y coordinates or z coordinate. We have to be only concerned with the x coordinate of the centroid. That is why this problem is very much simplified. So, you take the centroid of the cylinder, that of the cavity and that of the conical portion. So these are the values obtained from the handbook. Well, for cylinders you know very easily, half the axial length. So 1.5 divided by 2, and similarly 2 meter is the length of the cavity, so 1.0, and for cone you can get it easily from the again handbooks, and then you take the moments. Okay. So total volume, so total first moment, that is you add up this column, so you get these values, and finally we get the x coordinate of the centroid of this composite figure as the first volume moments divided by the total volume, and it will come out to be 1.0372 meters. So you have seen that how we can in a systematic manner calculate various centroids, etc. That was for the 3-dimensional case. Starting from area, that is 2 dimension, we went to 3 dimension, and sometime we have to do the similar exercise for the 1-dimensional case or a curvilinear body, a simple curve. So that will be centroid of a line or a curve in a plane. This line or curve is lying in a plane. Of course, if it is a helical type of thing, then it is a 3-dimensional curve, which we are not including over here, but it can be easily extended to 3 dimensions. So at the moment we will be concerned with the 2-dimensional curve, either a straight line or segmental line or a curvilinear figure. So here, for example, we have a curve, and a small arc length of this curve is of length ds is shown over here. The position vector of the center of this small length ds is vector r. Okay. So this is vector r whose coordinates are x and y, and this is the origin O. Now by definition and by analogy to the other centroids, we will have xc as x into ds, and this is the line integral divided by the total line length, and similarly yc will be y times ds line integral divided by total length L. Now one interesting thing is that whereas in the area integral and volume integral the centroid was inside the area or inside the volume, in the case of line integral, in the case of centroid of a line, the centroid can be, need not be always on the line. It can be outside the line, over here or over here or over here. It can be on the line also, but that is not always the case. Okay. Again, I will illustrate this with the help of a simple example. Suppose our line consists of 3 or 4 pieces of straight line or segments. So C1, C2, C3, C4. For each segment, centroid is half the length. Okay. So and then you can find out the centroid of the entire composite line. This is at point C. How to calculate that? Well, you use the formula over here. That is, for example, here is length C, first segment, whose centroid is over here. So I can calculate the x coordinate and y coordinate of the centroid, substitute over here. Second length, again third, fourth, and then you add up, divide by the total length of the line, and that will give me xc and similarly yc. As I said, it may be a point somewhere here or over here or over here, so that does not matter. Okay. Now The next thing we will do is some important theorems using these concepts of centroid, and in these theorems we can go from we can correlate two-dimensional figures with the corresponding three-dimensional volumes, or one-dimensional figure with the corresponding two-dimensional area. And these are for the surfaces or volumes of revolution. Now, let me define what is a, first of all I will consider the surface of revolution. Suppose there is a curve, any arbitrary curve and one axis. Now, let us say it is maintained at a particular distance from the x-axis, and then it is rotated about an x-axis. Then the curve will generate a surface which will be called the surface of revolution. You look at this. Suppose this is your x-axis and this is, here I am using a straight line as my curve. So if I rotate it about x-axis, so this will generate a cylindrical surface. All right. So this is called the surface of revolution. Now, theorems of Pappus and Guldinus, they relate the volume, the surface area of the area of the surface of revolution with the circumference on which the centroid of the curve, generating curve, moves. And similarly, we can go to two-dimensional case. Suppose here is a given surface and I rotate it about the one of its edges like this. So this will generate a volume. So this will be called the volume of revolution. So again, this volume of revolution can be obtained in terms of the area of the generating surface and the length of the curve on which the centroid of this area is moving. So these two very useful theorems will correlate to a one-dimensional body with this area of the surface is two-dimensional, and similarly a two-dimensional figure or geometry, that is an area with the volume of the generated body. After discussing the centroid of volumes and centroid of lines, now we will come to theorems of Pappus and Guldinus. These theorems relate a surface of revolution, I will explain what is surface of revolution, to its generating curve, and a volume of revolution to its generating area. Remember, surface of revolution is a two-dimensional configuration. So surface of revolution is correlated to the generating curve, which is a one-dimensional manifold. Similarly, volume of revolution is related to the generating area, which is a two-dimensional manifold. Now, what is a surface of revolution? For example, suppose there is an axis, x-axis, and a curve which is this x-axis and the curve, they are coplanar, they are lying in one plane. So now here in this example I am taking this curve as a straight line, but it can be any curvilinear line. Suppose keeping the x-axis fixed, this is rotated as if by a machine, keeping the distance same. So then this curve will generate a surface this surface is a surface of revolution. I give you another example. Suppose this curve is a generating curve is a slant line, again a straight line, but at an angle. So, if I rotate it, I will be generating a conical surface. All right. So, suppose this is a curvilinear line, a semicircle. Then, if I rotate it, I will be generating a spherical body. Okay. So, in this way, these are the surfaces of revolution. On the other hand, if I consider an area, let us say a rectangular area like this page, and take this as the axis of revolution, and if I rotate it about this axis of revolution, then I am generating a cylinder, a 3-dimensional volume. Okay. So, this is the generated volume and the generating area is a rectangle. So, a 2-dimensional manifold generates a 3-dimensional manifold. So, the theorems of Pappus and Guldinus will give us a very simple way to correlate the volume of revolution with the area of the generating surface, and on the other hand, the surface area of the generated surface with the length of the correlated with the length of the generating curve. We will take up these discussions in a detailed manner in the next lecture, and for the time being we will close today's lecture. Thank you very much for your attention.